Welcome to Learning Outcome 2, where we move from bodies at rest to bodies on the move. This is dynamics, how forces make things go, and we'll cover motion in a straight line and motion that turns, along with friction, momentum, and energy. So what is dynamics all about? In short, it's the study of how forces cause bodies to move. We split it into two halves: kinematics, which just describes motion, and kinetics, which links that motion to the forces behind it. We'll deal with two kinds of motion: linear, in a straight line, and rotational, turning about an axis. And the lovely thing is that both obey the same underlying laws. Engineers use exactly these tools to design vehicles, machines, and mechanisms. And this outcome builds them up one at a time. Let's settle some vocabulary first. Displacement is the change in a body's position, measured in meters. Velocity is how fast that position changes, in meters per second. Acceleration is how fast the velocity itself changes, in meters per second squared. Force is the push or pull that alters a body's motion, measured in newtons. And mass is simply the amount of matter in the body, measured in kilograms. Let's firm up velocity and acceleration. Velocity is displacement divided by time. Acceleration is the change in velocity divided by time. That's the final velocity minus the starting velocity, all over the time taken, where we call the initial velocity u and the final velocity v. When the rate of change is constant, we say the acceleration is uniform. And a deceleration is nothing more mysterious than a negative acceleration. One value worth remembering is the acceleration due to gravity near the Earth, about 9.81 meters per second squared. For motion with constant acceleration in a straight line, we have a neat set of tools called the Suvat equations. The first says the final velocity equals the initial velocity plus acceleration times time. The second gives displacement as ut plus a half at squared. The third links the velocities and distance. V squared equals u squared plus 2as. And the fourth gives displacement as the average velocity, a half of u plus v, times time. The letters stand for displacement, starting velocity, ending velocity, acceleration, and time. Let's try one. A car starts from rest and accelerates steadily at 3 meters per second squared for 8 seconds, and we want its final speed and how far it travels. Since it starts from rest, u is 0, a is 3, and t is 8. The final velocity is u plus at, which is 3 times 8, so 24 meters per second. The distance is ut plus a half a t squared. The first term is 0, and the second is a half times 3 times 8 squared. That's a half times 3 times 64, which comes to 96 meters. So the car reaches 24 meters per second and covers 96 meters. Now for the three laws that underpin everything in dynamics. Newton's first law says a body stays at rest or keeps moving steadily, unless a resultant force acts on it. That's the idea of inertia. The second law says the resultant force equals mass times acceleration, and it's the one we use to actually calculate forces and accelerations. The third law says every action has an equal and opposite reaction. Together, these three are the foundation of every problem we'll tackle. Let's apply the second law. A car of mass 1,200 kilograms feels a resultant driving force of 3,600 newtons, and we want its acceleration. Since force equals mass times acceleration, the acceleration is force divided by mass, so 3,600 divided by 1,200, which is 3 meters per second squared. In plain terms, the car gains 3 meters per second of speed every second. Let's talk about friction. Friction is a force that opposes relative motion between two surfaces, and it always acts against the direction you're moving or trying to move in. It costs us energy as heat, and it wears components down, but it's far from all bad, because brakes, tyres and clutches all depend on it. We work it out with friction force equals mu times n, where n is the normal reaction pressing the surfaces together, and mu, the coefficient of friction, is just a number with no units. Let's look more closely at that coefficient, mu. It's a measure of how grippy two surfaces are together. A larger mu means more friction for the same normal force. On a level surface, the normal force is simply the weight, mass times g. It's also worth knowing that static friction, before anything slides, is usually a bit greater than kinetic friction once it's moving. As a feel for the numbers, steel on steel is around 0.6, and rubber on a dry road about 0.8. And since mu is friction force over normal force, it's really just a ratio. Here's a worked example. A steel block of mass 20 kilograms sits on a horizontal surface with a coefficient of friction of 0.35 and will take G as 9.81. First, the normal reaction on a level surface that's mass times G, so 20 times 9.81, about 196.2 newtons. Then the friction force is mu times n, that's 0.35 times 196.2, which gives about 68.7 newtons. So you'd need a horizontal push of a little over 68.7 newtons just to get it sliding. Let's set the stage for rotation. Instead of distance, we talk about angular displacement, theta, the angle turned, measured in radians. Angular velocity, omega, is the rate of turning in radians per second, and angular acceleration, alpha, is how quickly that rate changes. For a wheel of radius r, the linear speed at the rim is omega times r. If you're given revolutions per minute, you convert to radians per second, using omega equals 2 pi n over 60. And it helps to remember that one full turn is 2 pi radians, roughly 6.28. Let's gather the rotational terms together. Angular displacement, theta, is the angle a body turns through in radians. Angular velocity, omega, is how fast that angle changes in radians per second. Angular acceleration, alpha, is the rate of change of omega in radians per second squared. Torque, tau, is the turning effect of a force equal to force times distance measured in Newton meters. Momentum, p, is mass times velocity, and impulse is force multiplied by time, which equals the change in momentum. It's really helpful to see linear and rotational motion side by side because they mirror each other beautifully. Where linear motion has displacement, velocity, and acceleration, rotation has angular displacement, angular velocity, and angular acceleration. Where linear motion uses force equals mass times acceleration, rotation uses torque equals moment of inertia times angular acceleration. And the first Suvat equation, V equals U plus AT, has an exact twin. Omega equals the starting omega plus alpha times t. Learn one column and you very nearly know the other. Let's look properly at torque. Torque is a force applied at a distance from a pivot, equal to the force times the perpendicular distance, so its units are Newton meters. That's why a longer spanner delivers more torque for the same push. In rotation, torque plays the role that force plays in straight-line motion. It produces angular acceleration through torque equals moment of inertia times alpha. That moment of inertia, I, measures how much the body resists being spun up. It's the rotational cousin of mass. Let's spin a flywheel. It accelerates uniformly from rest to 150 radians per second in 10 seconds, and we want its angular acceleration and the angle it turns through. The angular acceleration is the change in omega over the time, so 150 over 10, which is 15 radians per second squared. For the angle, we use the rotational version of ut plus a half a t squared. Since it starts from rest, that's a half times 15 times 10 squared, a half times 15 times 100, which is 750 radians. So it accelerates at 15 radians per second squared and sweeps through 750 radians. Now, momentum and impulse. Momentum is mass times velocity, measured in kilogram meters per second. When a force acts over a period of time, it changes that momentum, and we call force times time the impulse. It equals the change in momentum. Rearranging, force is the rate of change of momentum, the change in mv divided by time. The neat consequence is that a longer contact time means a smaller force for the same change in momentum, which is exactly why crumple zones and airbags work. They stretch out the time and soften the force. Let's put numbers to it. A 0.15 kilogram ball hits a wall at 12 meters per second and bounces straight back at 8 meters per second, with the contact lasting 0.02 seconds. Take the approach direction as positive, so the rebound velocity is -8. The change in momentum is the mass times the change in velocity, 0.15 times -8 minus 12. That's 0.15 times -20, giving -3 kilogram meters per second, a magnitude of 3. The average force is that change divided by the time, 3 over 0.02, which is 150 newtons, directed away from the wall. This leads us to one of the most powerful ideas in mechanics, conservation of momentum. In a closed system, the total momentum before an event equals the total momentum afterwards, provided no external resultant force acts. For two bodies, the mass times velocity of each one before adds up to the same total after. It applies to collisions, to explosions, and to recoil. Just remember, momentum is a vector, so directions and signs matter. And used carefully, it's a wonderful tool for cracking collision problems. Let's connect momentum with energy in collisions. Momentum is conserved in any collision with no external force, but energy behaves differently depending on the type. In an elastic collision, kinetic energy is conserved too. In an inelastic one, some kinetic energy is lost to heat, sound, or deformation. And in a perfectly inelastic collision, the bodies stick together and move off as one. Underlying it all is conservation of energy. Energy is never created or destroyed, only transferred. Recall too that kinetic energy is a half mv squared, and potential energy is mgh. Here's a classic. A 2,000 kilogram truck rolling at 5 meters per second couples onto a stationary 1,000 kilogram wagon, and we want their shared speed afterwards. The momentum before is the truck's 2,000 times 5 plus the wagon's, which is 0, so 1,000 kilogram meters per second in total. After coupling, they move together with a combined mass of 3,000 kilograms. Setting momentum before equal to momentum after, 1,000 equals 3,000 times v, so v is 1,000 over 3,000, about 3.33 meters per second. That's a perfectly inelastic collision. They carry on as one. Let's use energy on a falling ball. A 0.5 kilogram ball is dropped from a height of 2 meters, and we want its speed just before it lands, taking g as 9.81. At the top, it has potential energy of mass times g times height, 0.5 times 9.81 times 2, which is 9.81 joules. As it falls, all of that turns into kinetic energy, a half mv squared. Solving, the speed is the square root of 2gh, that's the square root of 2 times 9.81 times 2, the square root of 39.24, about 6.26 meters per second. Let me give you a dependable method for any dynamics problem. First, read it carefully and sketch the situation with the forces marked on. Next, list what you know and identify what you're after. Then choose the right principle. SUVAT, force equals mass times acceleration, momentum, or energy, and write down its formula before you touch the numbers. Substitute your values with consistent units and calculate. And finally, check the answer is sensible and quote the units clearly. Let's follow that method on a braking car, and notice we use two principles. A 900 kilogram car doing 20 meters per second brakes to rest in 4 seconds. First, the equations of motion. The acceleration is the change in velocity over time, 0 minus 20 over 4, which is minus 5 meters per second squared. The minus sign just tells us it's slowing at 5 meters per second squared. Second, Newton's second law, force equals mass times acceleration, 900 times minus 5, that's minus 4,500 newtons. So the braking force is 4,500 newtons, acting against the motion. Let's test what's stuck. First, can you state Newton's 3 laws of motion in your own words? Second, if a body speeds up from 4 meters per second to 20 meters per second in 8 seconds, what's its acceleration? Third, can you write the friction equation and say what mu represents? And fourth, what's the difference between an elastic and an inelastic collision? Have a go before moving on. A few more to try. First, a 3-kilogram mass moves at 6 meters per second. Work out both its momentum and its kinetic energy. Second, which principle would you reach for on a collision problem and why? Third, a wheel turns at 600 revolutions per minute. Convert that to an angular velocity in radians per second. And fourth, can you list the 6 steps for solving a dynamics problem?